the Gauss elimination method. So Gauss-Jordan method is an extension of that method and having additional steps. Okay, and Gauss-Jordan method has two applications. One application is for solving the system of equation. Another application is finding inverse of a square matrix. A, right? So we know finding the inverse of any matrix A, which is of size n cross n. First we will find determinant of A. If determinant of A is 0, then inverse does not exist. If determinant of A is non-zero, then we can talk about the inverse, and then inverse formula can be obtained using A inverse, adjoint of A divided by mod of A, right? But now we will use Gauss-Jordan method for finding the solution, finding the inverse of a given matrix, right? This is an alternate method to find the inverse for a given matrix, not using this formula. Okay, so which we will discuss later, but now in this talk we are going to use the Gauss-Jordan method to solve the linear system of equations. Okay, so in Gauss-Jordan elimination we solve linear system by Gauss elimination method, reducing the system into echelon form and then finding the solution by back substitution, right? So generally in Gauss elimination what we do, we find a triangular system, right, using elementary row operation, and then do back substitution. So here we are not going to do back substitution. We perform further reduction, that is a special case of echelon form, right, which is so called the name as reduced row echelon form, and then we read out the solution directly. Okay, we will see how we are going to read out. So first we will see a matrix is said to be reduced row echelon form if the first non-zero entries in each row is 1, and more important, the most important point here is in Gauss elimination the leading element or pivot element need not be necessary to be 1, but in Gauss-Jordan we will always make leading element to be 1. Okay, this is very, very important. This is important actually. We need to make it to 1 actually. Okay, and then the all entries above and below. So we know in Gauss elimination the all entries below the pivot entries are 0, but additional step in the Gauss-Jordan is above pivot entries all element must be 0. So we are reducing the matrix into an identity matrix type, okay, in Gauss-Jordan method. And similarly this any let I less than k if the first non-zero entry of row I occurs in the column ji and the first non-zero entry of row k occurs in the column jk, then we always have ji is less than jk, right? This is the way how the echelon form is being performed. Like for example, you take first row first column and look at it, that entry is to be 0 or not. If non-zero, then we are fine, we will make it to be 1 using elementary row operation, and then we switch to the next column and lower row, and in a similar manner like that, right? The 0 rows occur below non-zero rows. This is always we keep in our mind. So in Gauss-Jordan method reduces the given system into reduced row echelon form and reads out the solution directly, right? To bring a matrix to reduced row echelon form, what we do first, we first reduce it to the echelon form, right, and make all entries above the pivot entries 0, right, and which we will do starting from the rightmost pivots, right? We are starting from the rightmost pivot and then reaching towards left side. Okay, so let us understand with example. Solve the following system by Gauss-Jordan elimination method. So x plus y minus z equal to 9, 3x plus 11y equal plus 3z equal to 21, minus 2x plus 4y minus 6z equal to 40. So first we create the augmented matrix A, the coefficient of A matrix, and column vector B. Okay, then you see this is the your pivot entry, and fortunately this is 1, so we mark it as pivot entry by red block, and then we make zeros in the same column for the below the pivot entry. So this 3 has to be make as, we will make as 0, and this minus 2 we will make as 0 with the help of elementary row operation. So now if you see, if I multiply 3 times to this row, this coefficient becomes 3, and then subtract the row 1 from row 2 to achieve 0 here, right? So the elementary operation is R2 minus 3 times of R1. Similarly, I need to make 0 also here. To have 0 here, we will simply multiply by 2 and add it to here. So this 2 elementary operation we will write here, and always you need to mention the elementary operation whatever you are applying on the matrix. So the obtained matrix will become 1, and then remaining entries are 0, 0. And correspondingly you will also apply on the entire row, right? On the entire row you need to apply exactly this row, right? So be very careful while doing your calculations. Okay, so now the second row is obtained like this. Now if you see, we will move to the next row, next column, and lower row, and then lower row entry is non-zero, so we have to make it to 1 because we are solving Gauss-Jordan method. Okay, so now we will divide 1 by 8, we will multiply 1 by 8 to R2, so that it becomes 1, and then leading coefficient is 1, and we will make it 0. So 6 times of R2 we are going to subtract from R3, so which will become 0 here. So now this 2 column is over. Now we will move to the third column and lower row, and then find this element. So first of all we will make it to be 1 after suitable elementary operation, and then we got all pivots in all the columns. Now what we have to do is, we start from the rightmost corner, rightmost column, okay, rightmost column, and make 0 above this entry. And then once this is done, we will start the next column and then make it 0 to this entry. So using elementary row operation, if you see 1, I want to make it 0 here, so we will directly add R1 plus R3, right? And we will just multiply 3 by 4 and then add it to your last equation, right? Multiply minus 3 by 4 and then add it to your second equation, so which is the elementary operation given like this. Okay, now what had happened, we are getting 0, 0 here. Now we have to target this pivot element, and above still non-zero entries are there. And what Gauss-Jordan method says, below the pivot and above the pivot all entries must be 0. So this entry still is non-zero, so we have to make it 0. So we simply subtract from R1 minus R2, so we will get 0, right? And R1 minus R2, if we do, then we are going to get here, if we do 1 1 0 4 and 0 1 0 3, we are going to subtract. So what had happened, 1 0 0 and 1. So which is going to be nothing but this column 1 0 0 1. Okay, and then now finally we are going to read out the solution. X equal to directly x equal to 1, y equal to 3, z equal to -5, and then unique solution exists. Okay, now let us do one more problem. Solve the following system by Gauss-Jordan elimination method. Okay, so this is a 3 by 3 system. First we will write the augment matrix. Once augment matrix is here, then since this is the first row first column element, this is 4, but we want 1. So what we need to do, we will multiply non-zero constant 1 by 4, which is non-zero constant. Elementary row operation says multiply any non-zero constant to any row. So we are going to multiply the first row to get it 1. So this will be 1 and 1 by 4, 0 and 4 becomes 1. Now since this is a pivot entry, then below the pivot everything must be, all element must be 0. So we use these two elementary operations, right, which are quite simple. And then we got the first pivot entry, below all the entries below the pivot are 0. Now we move to the next row, a next column and lower row, and got this entry. We will be doing it as 1. So we'll multiply by -4 by 17 so that this coefficient become 1, and this is important only in case of Gauss-Jordan if you are solving. So this becomes 1, and then all the rest of the elements are get changed now, right? And then now you make 0 to the below pivot entry. How to make the 0? We have applied -17 by 4 into R2 and then added it to, subtracted from R3, right? So now if you see, we have reduced this to 0. Now we will move to the next column and lower row. Next column lower row is already 0. So in this third column no pivot entries is being obtained. Okay, and if the third column has no pivot entry, then this variable will be treated as free. So this is a clear indication of your infinite solution. Okay, but anyway, we have to make the proper your Gauss-Jordan method. So below the pivot all entries are 0, and above the pivot this entry is not yet 0. So we have to make it 0 using suitable elementary operation. 1 by 4 times of R2 and subtract it from R1. So this is your, above the pivot all entries are 0 and below the pivot all entries are 0. So now this is RREF reduced form. RREF form, right? So now we are going to just write the solution. X plus 1 by 17 y 1 by 17 z equal to 14 by 17, and y minus 4 by 17 z equal to 12 by 17, right? So we are going to send them z other side. So this is your solution where z is free variable. So if you plug z equal to 0, for instance, you will get z equal to 0 if you plug. So you will get x equal to 14 by 17, y equal to 12 by 17, right? And z equal to 0. So this is one solution. Similarly, you can find other solution as well. Okay, so thank you very much.